There we go. Awesome. Okay, so we've spoken about gas pressure. We've looked at all the gas laws, Boyle's, Charles, Avogadro's ideal gas law. Use the ideal gas law in terms of chemical reactions, finding amounts of reactants and products. And we've done the Dalton's law. We've done the partial pressures at the end of last week. So we have just one more topic left with chapter 10. And that is the kinetic molecular theory of gases, which in a sense we've been covering already. When we describe the properties of gases, we often invoke aspects of the kinetic molecular theory. Okay, so let's talk about this. This is section 10.6. It's the final section we're going to cover. We're not going to do 10.7, which is a more advanced gas law, van der Waals. So let's see. It's the kinetic molecular theory of gases. Now that's a mouthful. So what we're going to do is we're going to just abbreviate it as KM theory. KM for kinetic molecular. Okay. And as the name suggests, it's all about motion. It's about the movement of molecules, kinetic molecular. And the idea is that if you have a container of gas molecules, so let's make it a nice rigid container made out of steel, like a steel cylinder, that if we imagine what a gas is, what a collection of gas molecules is it's widely spaced tiny particles that are in constant motion, meaning that they do not stop moving. They are always moving. So this one, I'm going to use arrows to represent it moving in that direction. This one's about to bounce against the wall. This one might be moving in this direction. It's about to bounce against the wall there. This one might be moving in this direction. It's pretty far away from them all, from the walls. And then maybe these two are going to collide with each other right here. There'll be a little collision there, and then they'll bounce off their opposite directions. Okay, so motion, all of them are in motion. And so one of the things we would say is that the volume of each particle is approximately zero. Approximately, meaning, of course, it can't be zero. It's a particle, it has some space, but they're so tiny, atoms are so tiny that in a large container, you wouldn't even notice what the volume of each molecule is. It's really, really small. Okay, that's what allows us to make this assumption in the ideal gas law. You know, if you think about it, this is describing a gas or a mixture of gases. We often say the volume of the gas is the volume of the container. Right? We just say, okay, we'll just figure out how big the container is, and that tells you the volume of the gas. Well, the reason that works is because we're assuming that the gas molecules have zero size, so the space they occupy is the entire volume of the container. Okay. Now we can describe pressure too. So the idea behind pressure is, how do you measure pressure? Well, often the way you do it is you measure what's happening to the walls. What kind of pressure is the gas exerting on the walls? So think of when you're blowing or you're inflating a tire. Initially, the tire is very loose and you can push the rubber in and out very easily. But as more and more gas gets into that tire, it becomes harder to push in on it. There's a pushing force back in the opposite direction. It's inflating and keeping that tire up at a high pressure. So the pressure is actually due to many, many collisions of the molecules with the walls of the container. So these molecules, boom. Now each one is really small, so it can't really exert much of a force on the wall. But if you have a mole of them, and every second a mole are colliding with the walls, that's a lot of collisions. And over time, what you'll see is an average, and it exerts an average force that becomes significant. In fact, we see that with atmospheric pressure. So every square inch of your skin is exposed to almost 15 pounds of force. So it's 14.7 psi, I think is the number I gave last week, 14.7 pounds per square inch. That means if you take a square inch of your skin, the air is exerting a force of almost 15 pounds. So summed up over your entire body, the atmosphere is actually exerting a pretty large force on the surface of your skin. Okay. Excuse me. Okay, so volume is very small. So there's the first one. Number two, the molecules are in motion, in random motion. I'm sorry, hold on one second. I'll be right back. Let me go get something for my cough. So the molecules are in random motion. So that means they're not moving all in the same direction. They're just moving randomly. And we would say that the collisions are elastic. So that means when the molecules collide, they don't really absorb each other. Like if you threw two sponges at each other, they would kind of stick together. What we're claiming is they just bounce off like hard balls. Okay. And here's probably one of the more important ones. The average kinetic energy of the gas is equal to, so I'm going to write E kinetic, and then I'm going to put a little line above the E to indicate average, is equal to 3/2 RT. Okay, so the notation that we're using here is kinetic energy is E sub K. And then since each molecule has its own individual velocity, its own individual speed, we talk about the average speed of the gas, not any one particular molecule. So we use a line above the E to indicate average. Okay, so the average kinetic energy is equal to 3/2 times R, where R is the gas constant. But for this particular equation, we're going to use a different set of units. Instead of using atmosphere liters, we're going to use joules. So it's a different value. Before we had 0.08205738338. This is going to be 8.314. And the units are joules, the energy units, right, per mole K. So it still has the same units in the denominator that we had before, the atmosphere liters per mole Kelvin. We still have the moles Kelvin, but it's going to be joules instead of atmosphere liters. And remember, we have this conversion. An atmosphere liter is equal to 101.325 joules. All right. So that's where the 8.314 comes. If you just take 0.082057338 and you multiply it by 101.325, you can convert that to 8.314 and you come up with this value. So it's more convenient to use joules because if you recall in chapter 5, joules, kilojoules, we didn't use atmosphere liters for energy units, we used joules. So that's why that value is used. So you have this 3/2 times the gas constant times the temperature. And then, since these are gases, right, with gases, you want to use Kelvin. So we're not going to change that, right? Temperature should be in Kelvin just as it was before. And what this says is the following. It's kind of interesting if you think about it. Suppose we were to put in temperature is 0. You would get 0 average energy, right? And that kind of makes sense, right? If none of the molecules are moving, or at least the average velocity is 0, on average, they're not moving. They wouldn't be moving at all. So this equation from that sense kind of in that context makes kind of sense. So there's essentially 4 points I'm making. The molecules are really, really tiny. They're moving randomly. When they collide with each other, they don't essentially transfer energy in the form of sticking together. So they just bounce right off of each other like hard balls. And then, and no energy is lost as heat when they collide. And then the average kinetic energy of these molecules is directly proportional to the temperature. So as the temperature increases, they have more kinetic energy. As the temperature cools down, they have less kinetic energy. And you can actually calculate the average kinetic energy by using this very simple equation, 3/2 RT. Now that equation doesn't tell you how fast any one molecule is moving. It just tells you what their average is. Okay. So let's take a look at what our first type of problem is here. Okay, so we're going to go directly into what's called, I guess, Graham's law, molar mass. Yeah, we'll see. Okay, so let's go through it now. I have to give you a little bit more background before I can look at that problem. Oops. Okay, so let's talk a little bit about the average kinetic energy. So E sub K for kinetic energy, and then a line, and then that's 3/2 RT. Okay, well, what does this say? It says that the higher the temperature of the gas, the more energy they have. But let's go back to one molecule. Let's imagine you have one particle, and we want to calculate its kinetic energy, E sub K. So this is for one particle. So that particle could be an atom, it could be an electron, it could be a bus, it could be a planet, it could be a star. Well, the formula for that is 1/2 times the mass times the velocity squared of the particle. V for velocity. So M is mass, and V is equal to velocity, speed, right? How fast it's moving. So the heavier something is, the more mass it has, the more massive it is, the more kinetic energy it has. But likewise, the faster it moves, the more kinetic energy it has. In fact, the kinetic energy is more affected by velocity than it is by mass. If you look at this formula, if I double the mass, that doubles the kinetic energy. But if I double the velocity, you're going to square that too. So it's going to make it increase by a factor of 4. So the speed is really important in terms of how much kinetic energy something has. Okay. So now here's what I'm going to do. I'm going to now say that suppose we have a large number of molecules. Okay. Well, now we have to start talking about averages. It's really the average kinetic energy again, because we're not just talking about one. So what I'm going to do is I'm going to show you the formula for a large number of molecules that involves temperature, mass, molar mass, and speed. Okay. So if you think about it, suppose we said that we want to calculate the velocity. Suppose we know the kinetic energy, but we want to calculate the velocity. What would you do? You would multiply both sides by 2. And that would give you mv squared. Then you would divide both sides by mass, m. So you'd have 2ek over m equals v squared. And then you would take the square root of both sides. So you'd have the square root of 2ek over m, and that would be your velocity. So what this tells you is the velocity is affected, or it's determined by the kinetic energy, but also by the mass. The mass is important. But now we have this thing over here too. So this doesn't have mass in it or velocity, but it has temperature, right? There's temperature in there. So that tells us if the kinetic energy affects the velocity, right? They're related. And the kinetic energy is related to the temperature. That means the velocity itself must be related to the temperature. And in fact, it is. The higher the temperature, the faster the molecules move. So what we can do is we can combine these two equations, and taking into account that we're not going to talk about one molecule. This equation is for one molecule, one particle, but we're going to have a large number of molecules. So let's use the mole. Let's say that the number of molecules we have is a mole. Okay. What you end up with is the velocity, the average velocity, is equal to the square root of 3r2 over the molar mass. Okay, so m is the molar mass of the gas. Okay, r is the universal gas constant. Again, 8.314 joules per mole Kelvin. And then T is the temperature of the gas in Kelvin. And you have this really nice little equation here. V, oops, with a line, is the average velocity of the gases, or of the gas molecules. So that equation has 3 components of it. One is it's using this equation here. It's also using this equation here. But it's also assuming that we're talking about the mass of 1 mole of a gas, not the mass of 1 atom or 1 molecule. So for that reason, it's the molar mass that we would use. Okay, so those 3 put into here gives you this equation. So if you know the molar mass and you know the temperature, you can figure out what the average speed of these molecules are. Now, let me show you a couple of graphs. We're going to go through graphs a little bit, but let me show you this one. So let's make this speed. So this is the increasing speed. So this is V, and I'm going to put it in meters per second, or the unit. And then this is the number of molecules. So how many molecules are moving at a speed? So imagine it this way. Suppose I put a little point here. What that would do is you'd say, oh, here's the number of molecules that are moving at this speed. So let's say this is like 10 to the 10th. That would mean 10 to the 10th molecules are moving at this speed right here. That would be that point. Okay. But if we have a collection of gas molecules, they're all moving at their own speeds, right? So what you get is you get something that looks like this. Looks a little bit like that. It looks like a skewed to the left normal curve. Okay. And so this is what's called a gas speed or velocity distribution. It's distributed. And somewhere around here is an average. It's a little bit beyond the peak because of the tail, but this would be the average, V average. Okay. So imagine this curve is really coming from, imagine that you could calculate or measure the speed of every molecule, and then you plotted it on a curve of the number of molecules at each speed versus how fast they're moving. And you get this distribution. Okay. Now, if we look at this equation, what it tells us is that since temperature is in the numerator, right? It's in the top. The larger that temperature is, the larger the average velocity is going to be, right? Like if I make this number here bigger, that's going to make this number here greater as well. Okay. So that means the hotter the gas is, the faster the molecules move. So I'm going to show that here. These ones are hotter, higher temperature, and they're moving on average, they're moving faster. But remember, it's an average. So some of them are still moving slower, but on average, they're moving faster. Okay. There's another relationship here, the molar mass. The molar mass is in the denominator, it's on the bottom. So the larger, the greater that value is, the smaller the average velocity is going to be, the lesser, right? Inversely proportional. So heavier gases move on average slower than lighter gases. So if you were to have a collection of oxygen molecules, which have a molar mass of 32 grams per mole, and compare that to helium gas, which is 4 grams per mole, if they're at the same temperature, the oxygen molecules would move slower. Why? Because they're heavier. The heavier they are, the slower they move. The lighter, the faster they would move, right? So if you put in a really small number down here, you're going to get a large average velocity. So you really have two relationships here that you want to be aware of. One is temperature. The hotter the gases, the faster they move. And molar mass. The heavier they are, the slower they move. Okay? There we go. So there's our two relationships. So I'm going to write that equation down on another slide. Because we're going to use it.
Can I ask really briefly, why is it something that you would really need to measure? I don't know if that's a silly question, but why would you need this to measure how fast gas is moving?
Well, it explains certain things. So for example, why does a helium balloon rise as opposed to an oxygen balloon? So if I blow up a balloon with oxygen, it just stays there. But if I blow it up with helium, the helium rises. And part of the explanation for that is the helium molecules or helium atoms are moving faster. So the speed in the relationship to mass is important. We also need to be aware, like suppose you have a tank and that tank is filled up at a low temperature, and then you move that tank to another room where the temperature is higher. You might expect that tank to behave a particular way. It might have a certain pressure, but once you've moved it into that hotter room, now the gas molecules are moving faster. The pressure is going to be much greater, or is going to be greater than it was when you initially started. So you might think, oh, I've got this particular pressure in here, but it turns out it's greater than that, and that might burst the tank. You could actually blow up the tank because the temperature is higher where you have it now than it was before, right? So that's one application. Another, historically, has to do with how you produce nuclear fuel. So nuclear fuel is typically uranium, which is mined from the earth. It's an entire chemical and physical engineering process to get the uranium purified, to turn it from an ore into pure uranium. But uranium actually is a mixture of different isotopes, and one isotope is heavier than the others. The lighter isotope you can use to make nuclear weapons, atomic bombs, and hydrogen bombs. The heavier one doesn't work for that. It's unuseful. So it's essentially a byproduct. So in practice, what they do is they use the fact that if you can get it into the gas phase, if you can make uranium a gas, what you can do is you can separate those two gases based on how heavy they are, because the lighter one, being a gas, moves faster on average than the heavier one. So you can now purify this radioactive substance that you can use to make atomic bombs. And so that's, when countries are developing nuclear weapons like Korea, North Korea is, Iran is, probably a few other countries are doing it, but we're not aware of it. What they're doing is they're separating the nuclear active material from the inert material by using what's called gas centrifugation and gas diffusion, which is essentially based on how fast these molecules are moving in the gas phase. So it has certain practical applications as well. But many times people have been hurt by tanks that explode, or, they don't explode because it's a chemical reaction, they just explode because of pressure buildup. And that pressure buildup is essentially due to how fast these molecules are moving, which is dependent on their temperature. Okay. All right. So let's take a look. So there's our equation. Again, there's no, based on my experience, there's no great symbol for molar mass. But the one that seems the most common is the uppercase script M for molar mass. So that's what I've seen, so sometimes people will use for molar mass, which I'm not opposed to that as well. That seems possible, but this is the one that you're going to see most likely. Okay, so there's our equation, there's our relationship. So the first question, now we can do the first question on Alex, which is, we're going to do an understanding of average molecular speed scales with temperature and molar mass. So temperature, so speed, average speed, temperature, and molar mass. Those are the three quantities that are in that one equation. Okay. So it says here to rank the samples of gas described in the table below in order of increasing average speed of the atoms or molecules in them, because sometimes they're atoms, right? So like helium is atomic, it's an atom, whereas oxygen is O2, so it's molecular. Okay. That is, select one next to the sample in which the atoms or molecules have the slowest speed. So 1 is slowest, 2 is the next fastest, 3 is the next fastest, and then 4 would be the absolute fastest of the group. Okay. Now, when you look at these problems, they're going to give you a lot of numbers in here, right? So, I guess you could, in theory, calculate the temperature of the gas, right? Because you've got moles, you've got N, you've got, the temperature is given. So what could you calculate? You calculate the volume, right? From the ideal gas law, P equals nRT. But you don't need to do that here. All we're trying to do is to figure out which one has the highest average speed. So the two factors that are important are temperature and molar mass. The higher the temperature, the faster they move on average. The higher the molar mass, the slower they move on average. So really what you want to do is you want to look for the gas that has the highest temperature and the lowest molar mass, and that will give you the fastest one. And then the one that has the lowest temperature and the highest molar mass, that will give you the slowest one. So let me show you again. Let's come back to that equation. So U average equals square root of 3RT over molar mass. So you can, in theory, if you know the temperature and you know the molar mass, you can just calculate it, right? You can just calculate what's going on there and then get your average speed and then rank them. That takes a while to do that, but you can do it that way. So let's come back here. So what do we have? The first one, again, you don't need to know the moles or pressure. It's the temperature that's important and what the substance is, because what the substance is will tell you the molar mass. Now, this is neon at 6 degrees C. Okay, so what can you do? You could calculate the molar mass of neon. It's 20.18 grams per mole. And the temperature is 6 degrees C. So you could calculate that as a Kelvin temperature. But notice 3 of them are at 6 degrees C. So these first 3 are all at the same temperature. This one right here is much colder. It's at negative 20. So that one's going to be probably the slowest. I'm sorry, that's probably going to be the slowest because it's at the lowest temperature. So you got neon, you got krypton, and you got xenon. So let's go through you have neon, krypton, and xenon. Those are the 2nd, 3rd, and 4th noble gases. Xenon is the 5th noble gas. It's down in the 5th. It's in the 6th row, I guess. And then you've got the first 3 are at 6 degrees C, and then the last one, the xenon, is at negative 20. So let me show you this one. I'm just going to go through and calculate it for you. Okay, so let's do the neon. So your average speed would be the square root of 3, 8.314. So that's your value of R. And then it's at negative 6. So remember, you got to add your 273. And then you divide it by the molar mass. Now for neon, it's 20.18 grams per mole. But in order to make the units work out for joules, a joule is a kilogram meters squared per second squared. It's not a gram meter squared, it's a kilogram. So to make the units work out, what you do is you take your molar mass and you convert it to kilograms instead of grams. So you get rid of the grams. And that's going to move the decimal point 3 places. Okay, so that's just to make the joules, to make the units work out for joules. So 0.02018. Okay, and then you'll get an average velocity out of this. So let's see what it is. It's 3 times 8.314 times, I'm sorry, was it 6 or negative 6? I put negative 6 there. It's actually just 6 degrees. I'm sorry.
It's 6 degrees.
Yeah, let me get rid of that negative. So just 6. So what is that? 293.15. And then you divide that by your 0.02018, and you get a big number, but you got to take the square root. Don't forget to take the square root. That's going to make it smaller, right? When you take a big number, you take the square root, it makes it smaller. So it's about 602.
Do you have to calculate it in this case, or can you just look up the atomic mass of the gases since they're all the same temperature?
And do the compare. Yeah, absolutely. You can do that.
Okay.
That would work. Now let's take a look at the second one. The second one is argon. Now the molar mass of argon is somewhere around 40. I think it's 39.95. Let me just make sure here.
I think it was Krypton.
Let's come back. 39.95, so that's correct. All right. Oh, you're right. It was krypton. So is neon Krypton, you're absolutely right. Thank you. And this one was also at 6 degrees C. Okay, so it's Krypton, yeah, not neon.
Yeah, the first one was neon, and then it was Krypton.
Let me just get a periodic table because we got to look up 3 of them anyways.
And then we had neon, Krypton, and then the 2 xenon gases. I think if I wrote it down.
2 of them are xenon, right? Okay. And I got to find one that actually has the molar masses on it. It's funny, when I first started using the internet for periodic tables, I could find one really quickly, but now it just, when you type in periodic table, there you get these sites where they're trying to sell you one. So the quality is really bad because it's just one to sell. So it's actually, I used to go to Web Elements, I guess. Maybe that's what I should start doing again. All right, I'm just going to do that. Web Elements. It's an old company. And they're still around. Okay, so here we go. So Web Element, let me show you this one here. It is 83.80. So that would be the molar mass of Krypton, 83.80. Okay. Now we're going to do xenon after this one. So let me just go ahead and put xenon up. So xenon at 6 degrees C, and the molar mass of xenon is 131.29 grams per mole. And then the last one is xenon at -20. There we go. That'll make it a little bit. Okay, so let's try the Krypton. So again, the average velocity of these gas molecules would be the square root of 3RT. So 3 times 8.314. Now the temperature again is 6 degrees, so that's 293.15. I'm sorry, 279. Did I get the right one? 279.15. Let me just make sure I did that first one right. 3 times 8.314 times 279.15 over 0.0218, and then take the square root. Oh, I got a different value now, 565. So I miscalculated that temperature. Okay, so this right here, when you add those together, that's 279.15. I think I put 293 or something like that initially. So that should be 279.15. And then same thing here, your molar mass is 83.80. So you just convert that to kilograms. And that's going to give you 0.08380 kilograms per mole. So 0.08380. And then you take the square root. So 3 times 8.314 times 279.15 over 0.0838, and then take the square root, and it looks like it's 288. Okay, so this is one way to do it. You're just kind of cranking through that formula and calculating. So the xenon, this would be 0.13129 kilograms per mole. And this would be 279.15 Kelvin. So your average velocity would be 3 times 8.314 times 279.15. Divide that by 0.13129. So you're dividing by a larger number, right? 0.13 is larger than 0.08. So the heavier it gets, the smaller that speed is going to be. So 3 times 8.314 times 279.15 over 0.13129, and you get 230. So it's getting slower, right? The heavier they are, the slower they're going to move. For those first 3, the temperature is the same every time. So if the temperature is the same, the only thing that matters is how heavy it is. So the heavier it is, the slower it's going to go. So that would be easy to rank those. But now look at this last one. The last one is the heaviest, but it's also colder. So this one you would expect to go slower than this one because it's the same gas, xenon, so it's the same weight, but it's colder, so it should go slower. So let's see if that's true. If we're at minus 20, that's 253.15 Kelvin, right? You add the 273.15. So now your average speed would be 3 times 8.314 times 253.15 divided by 0.13129. And let's see what that works out. 3 times 8.314 times 253.15 over 0.13129, square root 219. Okay, so you can absolutely, what you could do is you could say, look, I don't want to go through this whole formula. I just want to use the two relationships, temperature and mass. So what I'm going to do is I'm going to say, oh, here's three gases at the same temperature. Sorry, 6 I didn't even write over here, did I? So those three are all at the same temperature. And this one's lightest, so that's going to be the fastest. This one's the next lightest, so it's going to be the second fastest. This is the third lightest, or the heaviest, so that's going to be the third fastest. And then this last one is the same one as the third one, but it's colder, so it's going to be slower. So this last one would be the slowest right here. And this one would be the fastest. So based on that, they said the fastest is 4 and the slowest is 1. And then you say, okay, well, what about the krypton? Well, the krypton is also at the same temperature, but it's heavier. So that's going to be 3. And the xenon is at the same temperature as the krypton. So it's heavier, but same temperature. So that's going to be 2. So the slowest is 1 and the fastest is 4. So either method will work.
Why is krypton turn out to be slower than the xenon if it's lighter than the xenon and at the same temperature? The ones where they're both at 6 degrees.
It's faster. The krypton's faster, 288.
Oh, okay. Yeah. Okay.
Yeah.
Oh, okay. It's just the rankings are in the opposite. Okay.
Exactly. Because I would have ranked it 1 is fastest.
Yeah.
And 4 is slowest. But the way they wrote the question was 1 is slowest and 4 is fast. I don't know, all relative is the scale, right? So yeah, so there you go. So either method will work. In a pinch, you can do the calculation. Now you can be clever about calculations too, because what you can do is you can say, look, if they just want me to rank it and not actually calculate the value, I could say that in each formula, 3 times R is the same. That doesn't affect anything. So you could just say, I'm not even going to use the 3 and the 4. I'm just going to take, temperature over molar mass. And whichever one, temperature over molar mass, is greater is going to be the fastest, right? And so you're doing that was what we would call semi-quantitative. You're not actually calculating the value, but you're calculating the ratio so that you can figure out which one is the fastest and which one's the slowest. Now, I do want to point out for a moment the units, because I kind of just said, hey, you got to have this in kilograms per mole instead of grams per mole so that the joules work out. But I want to show you how the dimensional analysis of this particular problem works. So remember, speed is distance over time, right? How far you travel divided by how long it takes for you to travel. So 30 miles per hour, 20 meters per second, length over time, okay? So in the SI system, the units that we use for distance is meters, which is abbreviated M, and time is seconds, which is abbreviated as an S. meters over seconds. So we want the speed to be in meters per second. So what happens is if we calculate this, and I'm just going to put the units in here. I'm not going to put the numbers and stuff. R is joules per mole Kelvin. And T is Kelvin, RT. And then molar mass. Now, what I'm going to do first, I'm going to use our traditional CGS system. Suppose I did grams per mole for molar mass, right? That's molar mass down there. I want to show you that this leads to a problem. And the problem is based on the definition of the joule. A joule is a kilogram meter squared per second squared. That's just the definition of what a joule is, and that's the traditional unit that we use for energy and velocity calculations. So here's what happens if I just leave that in there. I'm going to take out the joule and substitute in there kilogram meter squared per second squared. Okay, and look what happens. Your kelvins cancel, that's fine. The temperature units cancel. The moles cancel, they're both in the denominator, so they cancel. But the kilograms can no longer cancel because you have grams down at the bottom, right, in the denominator. So, what would happen is if you didn't do that molar mass conversion into kilograms per mole, you'd have an extra kilo in there, which is 1,000, and your answer would be off by a square root of 1,000. So by converting grams per mole to kilograms per mole, what that does is it ensures the kilograms cancel. So what does that leave you with then? It leaves you with meters squared per second squared. Everything else cancels out. So then the square root of something squared, right? The square root of x squared is just, well, technically it's plus or minus x, right? But we'll just say it's x. So same thing here. The square root of meters squared per second squared is just meters per second. So to get the units meters per second, you need to have that in kilograms per mole in the denominator. And suppose I said, well, wait a minute. Suppose I know it's RT over molar mass. Suppose I did liter atmospheres for R. And then, kilograms, suppose I did kilograms per mole. Well, now you got this kind of weird situation. What are these units? Like what's the square root of an atmosphere? Well, it's the square root of an atmosphere. So what this would do is you would be able to cancel out the moles. You'd be able to, and the Kelvin, but you'd have the square root. Well, let me write it this way. You'd have the square root, which is written as a half, of liter atmospheres per kilogram. And that would be your units of velocity, which in theory could be the units of velocity, but it looks kind of crazy, right? So for that reason, that's why we use the 8.314 instead of the 0.082057 for R. Joules per mole Kelvin. For those of you that have taken physics, you realize that, the dimensional analysis is important. Like if you want to know what the speed of something is or what the energy is or the force of something is, you really have to pay attention to those units. So that's what we're doing here in that calculation. Okay. All right. So that's the way to calculate it. That's a way to kind of estimate it. Let me go to the next. That's a nice periodic table, but I'm going to get rid of it. Let's go to the next one. Here we go. I like this one. This is a nice little problem here. So the next one is interpreting the graph of molecular speed distribution. So I talked about that a little bit earlier, right? This distribution, the idea that when you have a gas at a particular temperature, there's a distribution of speeds. So some are moving faster, some are moving slower. It's interesting to note that these speeds, so this is Krypton. We talked about Krypton a little bit earlier. And this is the temperature right here at 15 degrees C. So that, it's probably pretty close to 15 degrees C outside right now. It's probably 17 degrees C, so it's pretty close. So that's a reasonable temperature, and it's a reasonable gas, doesn't have a crazy molar mass. This is how fast those molecules are moving. And these are hundreds of meters per second. Now, if you want to just do a quick little estimate, if you take a number in meters per second, you want to know how fast it's going in miles per hour, you just multiply by 2, and that'll give you a rough estimate. So if a gas molecule is moving at 500 meters per second, multiply by 2, you get 1,000. That's 1,000 miles per hour. And so what you find is that with gases, even at room temperature, they're moving at hundreds of miles per hour, even thousands of miles per hour. So even if the ones over here that are moving slow, these ones are the slow ones, right? 100 meters per second is still 200 miles per hour. So gas molecules in the air are striking your skin and your clothing at hundreds of miles an hour. But because they're moving with such low masses, you wouldn't feel the actual speed of one molecule, but you do feel it as an air pressure. Those collisions they average out to a very measurable air pressure. Okay. So let's take a look at this graph. It says, use this graph to answer the following questions. Really, all we're doing is just reading off the graph. This is just reading off the graph. That's all you're doing. Okay. What is the most likely speed? The most likely speed of a krypton atom in the sample. The most likely speed is the most probable, and that's the peak of the curve. So you just look for the peak. It looks like the peak's up here. So it says to answer within 25 meters per second. And so here's your speeds here. So it looks like every square is a 50, right? 0, 50, 100, 150, 200, 250, 300, 350, 400. So the most probable is up here. And that looks like it's about 250 meters per second right there. Okay. Now you might say, well, what about over here? Well, that would be, 225, I guess, so 225 to 250, somewhere around there would be your most probable, most likely. So that's the peak of the curve. And then what higher speed is only half as likely? So half as likely. So here's the probability. The probability that gas molecules are moving some speed. So here's your peak. That's your most likely. Half that likelihood would be halfway down. So I think that's 10 squares if you count up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So half as likely would be 5 squares, half of 10, right? So you go down half the way. So that would be right there. Now, there's actually 2 velocities at that likelihood. There's one there, but that's lower than the most likely speed. The most likely speed is, 250 meters per second. This is only 125 meters per second, or 120. So that's below. You want the one that's higher, above. So you come all the way over to here. And so I'm 5 squares up. That's half the likelihood. And it looks like that's a little bit below 400. So I would say about 390, right? Because the next line over is 350. And this is much closer to 400 than it is to 350. So around 390. It's going to give you a little bit of leeway. It says you can be within 25 meters per second. So if you said 380, 390, you're going to get a correct answer for that one. Okay. Let's look at one more real quick. Probability. So what is the most likely speed of xenon in this particular? Now notice this is negative 140, very cold. And xenon, which is heavy. So they should be moving slower, right? Heavier, colder, slower, and they are. If you look at the scale here, 1, 2, 300, not 400, 500. So they are moving slower. So the most probable, that's up here, that looks like maybe about 130, right? Because it goes 100, 150, 200. So it's right there. I guess you could say it's right there too. So even if you said right there, that would be 125 meters per second, right? It's pretty much the same around there. And then what higher speed? So again, over here, higher than the most probable, is only half as likely as the most likely. So half, again, they made it 10 squares, 2, 4, 6, 8, 10. So you go down to square 5, which is right here. So then you read across, looks like it's right about there. So a little more than 200 meters per second. 210 maybe? Maybe 205, 205, 210, something like that. That would be half as probable. Okay. So there's that one. And then the last one of this, I think, is just calculating, which we actually just went through. Okay. Let me share this one. So calculating the average molecular speed of atoms in a sample of Krypton at 0.15 atmosphere at 9 degrees C, round your answer to 3 significant digits, okay? So don't be turned off by this root mean square term, RMS. It's not a statistics class. The root mean square is a particular type of average where you take one value. So you're probably used to what's called a simple average. So if I have 3 measurements of the same thing, so let's say I count the number of people in the room and I want to find out what the average number of people in these 3 rooms are. So I got 3 rooms. So how many are in this room? How many are in that room? How many in the third room? Okay, so I count the first one and it's 20. I count the second room and it's 15. And I count the third room and it's 25. The simple average is you would add the total number of people, 20 plus 15 plus 25, divide by 3, right? You add them all up and you divide by 3. That's called the simple average. The RMS average is what you would do is if you're measuring a bunch of different things, you're measuring a property about all of them, but they're all different things. It's very common to do what's called the root mean square average, which is a little bit more complicated than the simple average. Here, what you do is you would take the first room and square it. So you would take 20 and square it. And then you would take the second room, 15, and square it. And then you would take the third room and square it. Then you would divide it by 3 and then take the square root. So you're squaring and then taking the square root at the end. So that's called the root mean square. And that's the type of average that is generally used for gases, okay? But you don't have to go through that calculation. It's just telling you that's how they calculated the average speed. So that formula that I gave you earlier, right here, technically it's used for RMS, root mean square. But it's the same formula I gave you earlier, 3RT over molar mass. Okay. So again, this one is Krypton. At 9 degrees C. Again, you don't need to worry about how many moles are in there. You don't have to worry about what the pressure is in there. It's really just the temperature. So there's your temperature in Kelvin. And then you need to know what the, what the molar mass is. Okay. Sorry. Molar. Should just have a little periodic table out for myself here. So molar mass is 83.80. Okay, so there's your molar mass in grams per mole. And then now you can use this formula. So again, a kilogram over 1,000 grams, and that's going to give you 0.08380 kilograms per mole. And then you can just do your average. 3 times 8.314 times 282.15, and then divide that by 0.08380. So 3 times 8.314 times 282.15 over 0.0838 square root 289. I'm going to round it to 290. And that would be in meters per second, just as we talked about it. Go back over. Okay. So 3RT over molar mass, make sure you're using the 8.314, convert the temperature to Kelvin, and convert the molar mass into kilograms per mole. And there you go. That's it, right? So that is the molecular kind of explanation for the behavior of gases. They're widely spaced, they're tiny, they move really fast. That allows them to exert pressures on containers. That allows them to, blow up balloons, burst into, to burst containers if the temperature is high enough, right? If you make the temperature really high, they move real fast and they have a lot of kinetic energy. And if they have enough kinetic energy, they can start ripping bonds. They can start breaking chemical bonds and stuff like that apart. So there you go. Okay. So that's it for chapter 10. The next topic in the course is chapter 6. We're going to go back to 6. And that is getting into the quantum chemistry. So tomorrow, what we'll do is we'll start talking about waves and electromagnetic radiation, which is light. We call it light. So we'll talk about waves tomorrow. And then on Thursday, we'll get into a little bit of the quantum theory that Einstein and Max Planck developed back in the early part of the 20th century, 1905, which was a revolutionary time period for science. So that's when all the modern physics that we deal with today, our cell phones, our communication systems, our HD TV, all that stuff comes out of the work that those guys did back in 1900 and 1905, developing the theory of the electron, developing the theory of the atom, and cosmochemistry, all that stuff that, understanding galaxies and all that stuff, that all came out of those guys' work back then. So we'll talk about that on Thursday, a little bit maybe tomorrow and a little bit on Thursday, and then we'll go into next week. And then chapter 6 is really amazing chapter because you're starting off with the description of the physics of waves of light, photons. And then by the end, we're looking at the actual electronic structure of the atom. We're looking at a modern theory of where the electrons stack up in an electron, in an atom. And that allows us to then, when we get to chapter 7 and 8, to talk about chemical bonding, like a modern theory of chemical bonding. And we'll get into that. And then that's the cool stuff. All right. So have a great day. And I'll see you tomorrow.
Thank you. See you tomorrow.
Take care.